Hello everybody, and thank you all for joining us for this webinar, which is titled A Quick Introduction to Geotechnical Limit Analysis. I'm Colin Smith, and today I'll be using limit state geo to highlight some of the main aspects of geotechnical limit analysis, including key concepts in ultimate limit state analysis as applied to footings, slopes and retaining walls. This presentation itself will run for 30 minutes and will include a few minutes at the end for questions. These can be posted via the question functionality that's provided in the webinar interface. If I don't manage to answer your questions, please feel free to get in touch on info@limitstate.com and we'll be happy to answer them in detail for you. Now, just to start off, it's useful just to put the software and ultimate limit state software into context. If you look at the geotechnical analysis software that's available, on the one hand, at the top of this slide, we have what we might call traditional software based on closed-form limit analysis solutions. These might be spreadsheets or method of slices type approaches for analyzing collapse states. And at the bottom right-hand of the screen, we have the more advanced tools based on finite elements, which can model any problem geometry and complex soil behavior, including deformation and collapse, but perhaps is better at modeling deformation. Filling the gap is computational limit analysis. This provides the geometry flexibility of finite elements, but retains the ease of use and simplicity of traditional methods. The only parameters you need are C, phi, and unit weight, and provides a fully flexible tool for analyzing the ultimate limit state or collapse loads in geotechnics. So that's a very quick introduction. We'll move straight on to demonstrating the software and looking at a range of ultimate limit state problems through examples. So what you can see on the screen here is a standard layout of the limit state geo software, number of buttons and windows around the screen. I'll describe these as we go along. If we want to start a new project, we click New Project button, and we get a quick create menu. Now we can select the empty project and draw our own geometry, but the software comes with quick build wizards which build standard geometries, and then these can be modified later. So we'll kick off with a simple footing. So this brings up a series of windows which allows us to define the problem. We can put some project details in, which we'll skip over. We can define the geometry of the problem. We'll leave that as a default. We can define material properties that go in the soil below a footing and also the footing itself. Again, we'll leave those as the default parameters. We can also put in a load. I'm going to change this. It's currently set as just a unit load. I'll make that 100 kilonewtons per meter line load applied to the top of the foundation. And then finally, we can set the partial factors. We'll come back to that later. So if I finish, the software's built the geometry. It's very simple geometry. We've just got a rigid block at the top sitting on a block of soil here. Now, anything we click on in the problem, its properties appear in the property editor up on the right. So if I click on this block of soil, its properties appear up here, and we'll come back to some of those other information, but the key thing here is this materials window. There's one material assigned to that block, and it's called footing soil. And if we look at its properties, we see it's got an undrained strength Cu of 50 kPa. And it's set at the moment always to be modeled as an undrained soil. So this is effectively a foundation sitting on clay. Now, in terms of load, this is a load applied to the footing. Again, if we click on those details, we can see that we've got a load of 100 kilonewtons per meter squared applied to that footing. And we have this setting here called adequacy true. This is a key issue in ultimate limit state analysis. When we're trying to analyze for the collapse state, we're trying to find the conditions at which collapse would occur. Now, anything that you design will normally be nowhere near collapse state, so we have to do something to the system to get to collapse. And that's usually related to our margin of safety or safety factor. So in this particular problem, what we need to do is ask the software, what do we have to do to that load of 100 to cause this foundation to collapse? Do we have to make that load bigger or smaller? and by setting adequacy equal to true there, that tells the software that it's that parameter we want to look at. So that's the setup. Now we just simply press solve, that's the green button up here, and the software very quickly identifies the critical collapse mechanism under that foundation, which is a classical parental fan, and tells us our adequacy factor on load here. So if you like, this is a factor of safety on the load. It's telling us that we have to multiply that load of 100 kilonewtons per meter squared by 2.6 in order to get collapse. And we could have worked that out using Tizargi's standard bearing capacity formula. If you're familiar with that, the solution is 2 plus pi times the undrained shear strength. So that's 5.14 multiplied by 50, which comes out just a fraction below 2.6. So we get very close to that answer very quickly. Now the software, once it's identified the failure mechanism, animates it in order to increase the understanding of what's going on. Strictly, that animation is only valid at the instant of collapse, but it's taken further than that just for clarity. So you get instances of blocks of soil sticking out where they and overhanging, but that's just a matter of the animation being taken beyond its limits of validity. Now, okay, so far we've just solved a very simple problem, which we could have done by Tizargi's bearing capacity formula. So it's often the non-standard problems that cause issues in analysis. So, for example, if we have a slope on one side, very easily we can modify the software just by clicking on it. Now we've got a slope on that side. What is the bearing capacity of this foundation? Software very rapidly finds the critical collapse mechanism. And this time we have an adequacy on the load of 2.25. So we've lost a little bit of capacity. We need a lower load in order for that system to collapse. Alternatively, if I revert back, we may have a situation where somebody comes along and digs a trench next to our foundation, so I can draw that in. If I click delete, that basically deletes that block of soil. And again, if I click solve, we get another quite simple mechanism in this case, and our adequacy factor is dropped to 1.2, so that's a significant drop, which means we still have to increase the load to cause collapse. So in effect, that system is safe. If that adequacy factor drops below 1, then it means that we actually have to reduce the load to get collapse, and that means that the system is unsafe. So that's a key issue you're looking for. If you set the parameters to your design loads, then if this number is bigger than 1, essentially the system is safe. Something needs to be increased to cause collapse. If it's less than 1, then it's actually things need to be reduced to get to a collapse state. Now, if I revert back to our original geometry, if we recall, the solution was 2.6. Just to really clarify, emphasize the point about adequacy factor, that basically means that we had to multiply this load of 100 by 2.6 to get collapse, which is 260. If I change this to 200, then we would expect to get an answer of 1.3, which is what we get. And another way of using the software, if we actually want to know what the actual load is for collapse, we simply set the load to unity, a value of 1, and then we're just saying what do we have to multiply 1 by to get collapse, and that gives us the actual load capacity. So in this case, it's coming out at that number of 260. And again, just to illustrate the point, if we double the soil strength, for example, I've got an undrained strength of 50 at the moment. If I make that 100, then we would expect the foundation to get twice its capacity, and the answer we're getting down here has jumped up to 520. So it all hopefully that gives you the clarity on this issue of adequacy. Now we've looked at a problem here analysing footing on clay. We can look at sand. So in the left-hand corner here, we've got a Materials Explorer, which has some built-in soils, fairly standard properties. We can create any soil material we like with any cohesion and friction, but we'll take this built-in material, loose sand, and just drag and drop it onto here and replace that. We're also going to have try and model a smooth base footing. So we're going to take this frictionless material and drop it on the base of the footing. And so now we have a smooth base sitting on sand. If I then solve the problem, we get a very different mechanism here. This is a foundation on sand. If you look at the animation, you'll actually see some of these blocks are sliding and coming apart. This is the software modeling dilation in the sand. The software uses plasticity model of the soil as its representation, and that requires a modeling of the friction as dilation in the classic theory of plasticity. Now, the accuracy of the solution is very much dependent on how the software solves a problem. So just to illustrate that, this isn't a finite element approach. This is an approach based on slip lines and nodes. So here I've plotted all the nodes in the problem, and what the software does is it connects every node to every other node with a potential slip line, and using optimization it picks out of that very large set of slip lines the critical set that will cause collapse. So if I click solve again, you'll see very quickly the nodes appearing and then the slip line pattern coming up. Clearly the accuracy of solution is dependent on the number of nodes you use. So we have a setting here called nodal density, gives us control over that. If I set that to fine, you'll see that I get more nodes, a greater density of nodes, and I get a finer collapse mechanism being identified, and the collapse load actually reduces a little, so it's actually gone down from 71 using that coarse setting of nodes to 65. And if I go to very fine here, I get even more nodes. And again, what the software is doing is it's fitting a collapse mechanism to that set of nodes. So it's very much fine than anything that you could hand. The mechanism you can see is getting more refined in this case. And we've got a collapse load of 62 here, which has just come down from about 65 from before. So basically we're a few percent change. So generally the software is very useful to use it in an interactive mode with maybe a medium or fine setting for the number of nodes. And then when you want to just pin down the answer, increase the number of nodes until you get a convergence of the load or the adequacy factor. Now that's a quick look at foundations. We'll now look at other problem types. So the software is fully general. It can solve any problem you care to draw. We'll just reuse the wizards as here. I'm just going to click finish for speed. So here we have a very steep slope. Again, this is an undrained soil. And in this case, generally with slopes, what we're interested in is not a factor on a load, but a factor on strength. So here we've actually set up here, we've got a choice between factor load or factor strength. So this is set on factor strength. So if I click solve, what the software is going to do is tell us how much we have to reduce the soil strength by to get collapse. So in this case, it's saying we have to reduce the soil strength by a factor of 2.47 to get collapse. And again, if I click on this and look at soil properties in the property editor, strength is 50, so that has to be divided by roughly 2.5. It needs to come down to about 20 for this system to collapse. And clearly, if I reduce that strength to, say, 25, then that factor will reduce. And now we're down to about 1.23, so we're much closer to 1. And this system is nearly on the point of collapse. I'll revert back to the previous setting. We can use this undo button to revert us back. So that soil strength is now reverted back to 50. Just to clarify the difference between factor strength, factor load, I could also ask the question, what sort of load could I put on the surface to cause collapse? So supposing I put a surface load of 5 kPa on the surface, and I'm going to put an adequacy of true on that. So I'm going to ask the software how much bigger does that load have to be to cause collapse. The wizard actually sets up adequacy also on the weight of the soil. I'm just going to set that to false at the moment, and I'll set this to factor load mode. So now we're asking the software, what do we have to do to that surface load to cause collapse? And it's telling us actually we've got a big margin of safety. In that case, we have to multiply that surface load of 5 kPa by 17.23 to induce a collapse. We can also, as well as applying those factors to surface loads, we can apply it to self-weight of soil, which is how the system is set up. So here we have self-weight loading, and here if I set that to true, then what the software will do is it will find that the number which we have to multiply that surface load and the weight of the soil by to cause collapse. And that's a much smaller number, 2.28 in this case, because obviously in this case the weight of the soil is what's dominating stability, whereas that surface load is actually relatively small compared to the weight of the soil on the slope. But in all cases our adequacy factor is bigger than 1, so we have a safe system. Now we can model solid blocks of soil, we can also model thin layers, so I can draw in, for example here, using a line tool, so it's this button here, a line, and I can actually put a material on that. So I could, for example, put a very soft clay, put that there, and oops, I've just missed in that case. So, yeah. So now I have a thin layer of weak clay. That could represent a pre-existing slip surface in a slope stability problem. Normally it might be curved. We can modify the geometry quite easily. And if I click solve, then what we find is the software identifies a collapse mechanism which is making use of that weaker surface, and we're getting a reduced adequacy factor on the load. So that is making a difference. Okay, so that's a very brief look at slopes, and again it's possible to modify the geometry, saying, well, what if we regraded that slope? What difference does that make to our collapse? So it's very easy to adjust the geometry, or we can indeed look at using this polygon tool. What if we put a berm at the base? Put a dense sand in there. How does that affect the stability? And we can see that in this case the adequacy factors improved to 3.2, whereas before it was 3, so a marginal change in that case. So that's a very brief look at slopes. We'll now look at retaining walls. So we'll look at a gravity wall problem. So the wizard again quickly builds us a standard geometry, but we can change the parameters very easily. So let's look at this problem. We're going to just preview the nodes to see where the nodes are. So we've got a certain density. It's a little hard to see the nodes on that base material. I'm just going to change the color of that base material, something slightly lighter, so we can see those. And preview the nodes again. Now what you can see is we put more nodes at the base here that the wizard has rather than under the wall, and so this is because we think there's more likely to be a more complex failure mechanism under the wall, and putting more nodes there gives you a much more refined mechanism. So if I analyze that problem, I just click solve again. In this case we're on a factor load, so what the software is doing is it's saying how much bigger does this surface load have to be to cause collapse. And it's saying we have to multiply that load by 20. And that load, if we click on it here, it's been defined as a variable load, and it's roughly 5 kPa on the surface. So again, we've got a very large margin of safety in that problem. In this case, it's a fairly simple mechanism. When the software has done the analysis, you can generate a report which gives you all the information about the problem. So it gives you the adequacy factor found, the collapse mechanism, and if you want, all the geometry and material properties. And also you can ask the software to actually give you the free body diagrams that you'd get if you were analysing this by hand. If it's only got 2 or 3 sliding blocks, that's something you can actually check by hand and get an understanding of what's going on. Clearly, if it's got hundreds of sliding blocks, that becomes rather intractable. But it is quite useful for if you want to do a manual check with conventional sort of hand calculation. Now, in this particular case, the mechanism just found a failure where the wall slid on the base. The software will identify the most critical mechanism that can be found, whether that's sliding or rotation or bearing failure, or a global failure. If this soil down here was a little bit weaker, so it's currently set at 50, if I set that down to 30, as a base strength, undrained soil, and click solve, the software is actually saying, actually we're more likely to get a global collapse mechanism and failure under the wall. So basically a sort of slope failure that's just going around the wall. However, you notice in this case the mechanism is actually hitting the boundaries of the problem, and if these are artificial boundaries not representing, for example, rock, then it's very important that the mechanism doesn't actually hit the boundary, so we need to move that up. So we can either drag or drop that, or we actually, whatever piece of geometry you click on, its geometry appears in this geometry editor, and I can, for example, move the x-coordinate of that boundary to -2. I tried to do that while it was still in a solved state, so we'll just repeat that. And the same with that one. And we solve that again. This time we don't hit the edge here. We get a slightly lower adequacy factor, but we're still hitting the base. Now that could be a real rock boundary, but maybe there's a deep deposit of clay there. So I can move the base down. I'll move that down to -2. And this time we get a mechanism which dives under the wall. It doesn't hit the base. Now it's hitting the edges. So again, we'd have to move the boundaries out. I won't do that now for time issues, but that's what you'd have to look at. So I'll just revert us back to our original geometry and original strength. One thing the software can do is it can do seismic analysis, so it uses a pseudostatic approach. We have this little setting here, seismic actions. And what I can actually do is put adequacy on, for example, horizontal acceleration. I'll put a 1 in there. I'm going to remove the adequacy from the load. That's false. And there's a very useful feature called diagnostics here, which if you click on it, it gives you an overview of the problem, some information, it tells you where you put adequacy, and you can look at this to check that you've applied it exactly where you want it. So this is saying we've just applied it to seismic body forces in the X direction. And it tells us a little bit about boundaries and so on. But it usually gives you a summary of what you've set up, and it's very useful just to check that you've set it up as you expect. So essentially we're asking the software what magnitude of horizontal acceleration is required to collapse this wall. And if I click solve, it's finding a much bigger failure mechanism as you'd expect in a seismic analysis. And the answer here in this particular case is saying that we have 0.88 G, horizontal 0.88 G is required to collapse this. Now clearly the mechanism is hitting a boundary, so it does need extending, but that's obviously quite a high G level. But you can use the software clearly to check on those on seismic stability. Okay, we'll just finish off by looking at a sheet pile wall. So again, we'll just use the wizard very quickly. This is a sheet pile wall. In the first instance, the wizard's built as a problem retaining clay. I'm going to click solve, and what the software is doing is saying how much heavier do we have to make the clay behind the wall to cause collapse. We can pose these collapse problems in many ways we like. This sheet pile wall is modeled using a special engineered element in the software, and it's able to model identify bending moments in the wall. And also here it's identified a tension crack because this is clay. The wall can quite clearly move away from the clay, and the clay will stand up. If we put sand, for example, behind the wall, then we don't get a tension crack. The sand will just follow the wall. We get a different mechanism, and we'll get a different bending moment distribution. Now, another point about ultimate limit state software, in this case, this is a bending moment distribution that would arise if we had a rigid wall, but rather than taking the bending moments from here, saying that's what we're going to design the wall for, it's actually better to get the software to find the collapse mechanism involving the wall, or identifying where a hinge might form. So we can set the bending strength of this wall, and the software can actually model bending of the wall. So here we've seen that we get bending moments of around about 48 at most. So what I'm going to do is click on the material here. This sheet pile, its properties appear in this window as well as in that if we click on it. So I've got sheet pile there. Currently it's got a bending strength moment resistance of 150. I'm going to set that to 25 and solve. And what you can see hopefully is that actually we get a different mechanism, and it's actually modeling bending just below the surface of the base material, which is a clay. We get a different bending moment which maximizes out at 25. So you can model structural failure in this type of software as well as soil failure. But again, the issue is to identify or define what margin of safety or what parameter you want, whether it's load or strength, and use that to clarify the problem. As we're towards the end of this webinar, just to explain one other issue here. Scenario Manager, we can actually define partial factors on materials. We have built into the software Eurocode factors, for example, Design Approach 1 Combination 1 and Design Approach 1 Combination 2. If we define those, and the software pre-applies these factors to the problem before analyzing, and we can also ask the software to choose between using undrained and drained properties of the soil, but I'll just set it for 2 here. So if I run this now, it's warning me that I've set non-unit load factors just in case I'd forgotten that I'd done that, and it will solve both problems and identify which is the critical case. Now this is preset for Eurocode, but it can be used for any other codes where you're pre-factoring either loads or material properties. And it's telling me that in this case Design Approach 1 Combination 2 is the most critical. I've got the lowest factor here. These are both less than 1, so this wall is clearly not stable. Partly because I set a very low bending strength in the wall. Okay, I hope that's given you a summary of, or an overview of the types of analyses that you can do in ultimate limit state software, an idea of the sort of issues that you need to be thinking of in this type of problem. So if I just go back to the slides for a summary, hopefully I've shown you that the software is interactive, solves quickly, so you can answer what-if type questions, get a feel for the problem. You can solve any problem type of any geometry. You don't have to impose any idealizations. You only need to put in strength of the soil, C, phi, and unit weight. It uses a plasticity model for the soil as its representation. And you can solve problems which are not just soil, but with soil reinforcement or structural elements. I've demonstrated a sheet pile wall. You can also model geotextile type reinforcement. Okay, well, we've just got a few minutes left. So happy to take questions at this time if there are any. Okay, we don't appear to have any questions coming up, so oops. All right, one question. Example of reinforced earth. I can do that fairly quickly. We have a wizard in the software which sets up reinforced soil wall. I'm just going to go with the defaults here. So this is one example. This is actually using the software to model rigid facing in a block of reinforced soil, and these elements here are using engineered elements which we can define pull-out factors and rupture strength in. So this is able to represent both soil nails or strip reinforcement as well as sheet reinforcement like geotextiles, and putting in the right mix of pull-out factors and rupture strength means we can model those problems. If I click Solve, the software deals with reinforcement fully flexible. There's no it doesn't internally work out pull-out lengths and so on. It just treats it inherently as part of the collapse problem and seeks out the mechanism which is most critical involving that reinforcement. So here you can see that we've got something that's broadly a two-wedge mechanism in this case. It's actually plotting the axial force in the reinforcement in this case. Here you can perhaps just see that we have some pull out of the reinforcement. This small element is pulling, so it's pulling out of the soil here. Higher up here, the soil behind the wall is actually following the reinforcement, so that's all coming with it. So it's modeling the full interaction, relative sliding of the soil with the reinforcement using the standard kind of models that are used in conventional reinforced soil analysis, but allowing it to be fully flexible. A couple of other questions. Will the seminar be available later? Yes, we will make a recording available. Can it be used to model a weak interformational layer in a dipping rock mass? Yes, you can model different layers in soil, and I'll just very quickly show that. As before, we can model thin materials, but you can put in, say, a thin layer of clay, and you could make that very strong. So if you can model the soil as a high C or high Phi value material, then you can model that. And yes, for dipping rock masses, you can model discontinuities in rock mechanics. Same way here. So for simple sliding problems, that is possible. Okay, I think that's covered all the questions, or the questions I have time for, so we'll just wrap up. So I hope you found this informative. If you're a current user of Limit State Geo, I hope you've learned something new about the software that you didn't already know. If it's prompted any other questions that I haven't answered, please feel free to get in touch via telephone or at info@limitstate.com, and we'll be happy to help. For those of you who aren't current users of Limit State Geo, we'll be in touch over the next few days to get some feedback, find out if you have any further questions, and see whether you think Limit State Geo will be useful to you. If you'd like to watch the webinar again, or you think you might know somebody who'd be interested to see it, there will be a recording available later this week, and we will email you with a link once that's available online. And also, please look out for any notifications regarding other events, or we'll send out via email or post it on our website at limitstate.com/events. Finally, I'd like to say thank you all for listening, and I hope you can join us again in the near future. Thank you very much.